Here's worksheet number 5, solutions. In here we're looking at linear higher order ODEs with constant coefficients. Okay. So one definition, and primarily what we'll be looking at is second order ODEs. Second order linear ODEs that are homogeneous. Homogeneous in this case means that the equation is equal to 0. It's a different definition of homogeneous than we used in the first chapter. But homogeneous means that you have y terms or y derivative terms, and they may be multiplied by some function of x. So a second order linear homogeneous differential equation could have a function of x times the second derivative plus another function of x times the first derivative plus a function of x times y is equal to is equal to 0. So if p of x, q of x, and r of x, if each one of these coefficients is a constant and not a function of x, then we have this equation down here where a, b, and c are just some numbers. And these are the simplest types of second order linear ODEs to solve. We can solve these by making a substitution, y equals e to the mx, and the equation will reduce to what's called an auxiliary or characteristic equation here. So let me show you how it reduces. Here I have y equals e to the mx. When I substitute in, I'm going to substitute in for y prime, and for y double prime. So I'm going to find my first derivative, y prime. Remember, to take the derivative of an exponential function, you want to take the derivative of the exponent, which is m. That comes down, and then your exponential function comes back. So y prime is m e to the mx. And our second derivative, y double prime, again I'm going to take the derivative of mx. That'll bring another m down. It'll give me m squared times my exponential, e to the mx. So when I substitute into my differential equation, here I'm going to write this as a y double prime plus b y prime plus c is equal to 0. Then making my substitutions, my second derivative becomes m squared e to the mx plus b. My first derivative is m e to the mx plus, that should be cy, plus cy, and y is e to the mx. And that's equal to 0. Now notice that we have the e to the mx in common. You can factor out the e to the mx, and that leaves you with a m squared plus bm plus c, and we get this product is equal to 0. This tells us that either our first factor, e to the mx, is equal to 0, or the second factor, am squared plus bm plus c, is equal to 0. Now, if you remember graphs of exponential functions, an exponential function is never equal to 0. You might have a graph that comes down and approaches 0, and it's a nice gentle curve, but it will never actually touch this x-axis, or the value of that function is never 0. You could have an exponential function that starts off here with a horizontal asymptote at 0, and it may increase also. But the point is that this function will never touch the x-axis. It'll get closer and closer, but it will never touch it. So e to the mx can never be equal to 0. This gives us no solutions. And so if we have any solutions to the differential equation, they have to be solutions to am squared plus bm plus c equals 0. That's called your characteristic equation.